Before going back to the momentum equations, I want to talk about the curl, the circulation, and the vorticity. I'm going to define the curl of a vector field in Cartesian coordinates. I'm going to write down what the expressions are, but the important thing to remember, or an important thing to remember, is that the curl of a vector is a vector, and a vector can be expressed in any old coordinate system. So even though I do things in Cartesian, there's nothing special about the Cartesian coordinates. The only reason I use it is because the expressions are easier to write in Cartesian coordinates. All right, so the curl of a vector, so the curl of a vector v is written as del cross v. And in Cartesian, this can be expressed using the usual expression that we use to take the cross product of two vectors, except the first vector now will not be a vector, will be a differential operator. So in Cartesian, I put the unit vectors, the coordinate unit vectors x, y, and z hat. In the first row, then the components of del, or which are going to be d by dx, which I write using a shorthand notation, which is just a partial with a subscript x. That's the partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And then in the last row, I put in the components of v, and I'll use u, v, and w, the usual components I use for the Cartesian components for the velocity, u, v, and w for v. Then I will evaluate what this expression is. So what I get is x hat times dw dy, and I use the subscript notation to mean a partial derivative with respect to y, minus dv dz. So right, the dw dy minus dv dz, minus y hat of dw dx minus du dz, plus z hat times dv dx minus du dy. And this can then be written as a column vector in Cartesian coordinate as dw dy minus dv dz, du dz minus dw dx, and dv dx minus du dy. And notice that I interchange the order of these two because of the minus. So minus makes it a plus, the uz as the plus, and the minus. Okay, so that is what computationally, what the components, the Cartesian components are of the curl of a vector field. And in the special case where the vector v is the fluid velocity, then this is called the vorticity. So if v is the fluid velocity, then the curl of v is called the vorticity. And so the vorticity is a vector, and it has three components, the x, y, and z components. And the way to think of it as a vector that is independent of the coordinates in which you measure it, you can imagine a little vorticity meter. So before I draw my vorticity meter, I'm going to copy the expression for what the curl of v is so we can have it for later. And I'll write it in red. So del cross v is equal to these three components, dw dy minus dv dz, du dz minus dw dx, and dv dx minus du dy. All right, now I'm going to draw what a vorticity meter looks like so you can have a sense of what it measures. So you can imagine taking a little paddle wheel. So I'm going to draw a little paddle wheel here. Arrow. Right. And now you can imagine dipping this little paddle wheel into the fluid and measuring the rate at which the paddle spins, right? So as it spins, you can measure it. And the rate of spin in the direction of the arrow is the component along that direction of the vorticity. So that's what a vorticity meter is. It's that little paddle. You stick it in the fluid. So you can imagine if you had a sheared flow like this, right? And this, let's say, is the z-axis, and this is the x-axis, for example, and I put my little paddle in here such that the arrow is pointing out of the board. So the arrow is coming out at us. Then the paddle will start spinning in this direction, right? And the rate at which it spins is going to be related to the vorticity in the direction coming out of the board, which is the minus y direction if we have the right-hand coordinates, right? If we have the right-hand coordinates, this is z, this is x, and the y-axis would be pointing into the board. So if our vorticity meter is pointing out this way, it would be the negative y component of the vorticity. If we flip the little vorticity meter so that the arrow is pointing into the board, then we would get the y component of the vorticity. And you can see that relative to y, it's going to spin apparently in the, we change the sign when we change the order of the arrow, right? If I put in the arrow in here pointing out, then it's going to spin clockwise, right? If I look into the board, it spins clockwise. But if I'm standing on the other side of the board and I'm looking at the same shear, it's going to be spinning counterclockwise, so you get the negative sign. All right, so that's one way to think about the curl. Another way to define it is so that it is it appears more coordinate independent is the relationship between what's called the circulation and the vorticity. So let's do that relationship now. Now if I take a fluid and I take a little patch of fluid or some surface, and to make it simple, I'm going to take the y and x axis, and I'm going to take a small little infinitesimal patch over here like this and define this point as x and y point, and then this width here is going to be delta x and this height delta y. So it's a small little patch of area dx times delta x times delta y, and what I want to compute is the circulation around the loop formed by this little frame here. So I can imagine having a little tube, a little imaginary tube along the edge here. It's an imaginary tube because it doesn't interfere with the flow, but then I impose, I put this little frame, this imaginary frame, inside the velocity field, and I also have vectors defined at every point in space. And then I take the component of the velocity field along the loop in the counterclockwise direction. And I integrate v dotted with the distance. So how the velocity times the distance around this side, the velocity times the distance or the speed along this direction times this distance, and I go along the loop. I do that integral. In other words, if I do this loop integral of v, the velocity vector, dotted with a little vector element of length dr, what do I get? So I'm going to get, if I go around in the counterclockwise direction, starting at the bottom, the component of the velocity along this side of the frame is going to be the u component, so that'll be u of x and y, multiplied, if I'm doing the loop integral, times delta x. Then I'm going to go up on this side, so the component along this is the y component, or v, so plus v. But now I'm shifted over from the origin by an amount delta x, so it'll be x plus delta x and y. So it's v evaluated x plus delta x, and then I multiply by the height, delta y. And then I come back along the top, so I have the u component again, but now I'm going in the opposite direction, so it's minus u. And now I'm no longer at y, I'm shifted up by a delta y. So it's y plus delta y times delta x, right? The length is delta x. And then I come down on this side, so minus v at x and y times delta y. That is what that little loop integral is. And the next thing I'm going to do is I'm going to replace this u evaluated at y plus delta y and this v evaluated at x plus delta x with their Taylor series, first order Taylor series. So let's write down what these are. All right, so I expand this one in the Taylor series. So this is v at x plus delta x and y is v at x and y plus dv dx times delta x plus terms of order delta x squared. Terms that are going to be small, that are going to vanish in the limit where delta x goes to 0. And then the u at x and y plus delta y is going to be u at x and y plus du dy times delta y plus terms of order delta y squared. Again, terms that vanish. So now I can replace this expression by this expression and this one by this expression. And so what I get is the loop integral of v dr is equal to, now if I combine these two first together, these two together, what I get is v at x plus delta x, y minus v at xy, all multiplied by delta y, plus or minus, so let me put a minus, make it simpler, minus u at x, y plus delta y minus u at xy, all times delta x. So I just copy this over, grouping terms, these terms together, and grouping these two terms together over here. Now I can substitute in more easily these expressions. So v at x plus delta x is v at xy plus dv dx. So when I substitute that in here, the v of xy terms will cancel. I'll have this minus that, and I'll be left with this expression. So what I have is dv dx times delta x times delta y, delta x, delta y. This, of course, is going to involve some terms of order delta y squared times delta y squared, times delta y. So terms of delta y cubed, which are even smaller. Maybe I can write it down, plus terms of order delta y cubed. And then the same thing over here, I will have minus, and this time when I plug this expression in here, the u of xy will cancel, and what I'm left with is du dy, times delta y and delta x, delta y, and this time I will have errors. Oh, I said delta y cubed, that's wrong. This should have been delta x squared delta y, and higher order terms, plus terms of order delta y squared delta x. The important point, though, is that I didn't need to copy those. These are going to go like the cube of small quantities, right? Delta x squared and delta y. So these are going to go to 0 very fast compared to these delta x, delta y. And so in the limit, what I get is, in the limit where delta a equal to delta x, delta y goes to 0, of the loop integral of v dotted with dr divided by the area is going to be equal to, if I divide the area, this delta x, delta y goes away, I get dv dx minus du dy, and this area goes away, and these terms are going to be of order, this one will be of order delta x, and this one will be a term of order delta y, and so in the limit, those delta x, delta y vanish, and I'm left with just this term, which you recognize now as being the z component, the z hat component of the curl of v. So the circulation per unit area around a small patch gives us, defines the curl, let me say it again. The vorticity at a point is the circulation per unit area around the little frame. So since it's a vector, I would take the a direction, and I find a little patch perpendicular to the direction, and then I calculate the integral of the vorticity in that direction perpendicular to that patch per unit area. So, sorry, the vorticity at that point, and that is the circulation per unit area around the little loop. And you can do this in every direction. So that kind of maybe gives you a little bit of a feel for what's the relationship between the curl, the vorticity, and the circulation. All right, now we're ready to use the curl on the momentum equation.